Hi everybody, this is Obi-Wan Pez for Simplex Pachinko. We are just currently waiting for Microsoft Whiteboard to start behaving itself. I could potentially use OneNote or something like that, but unfortunately that has my name plastered all over it, and I don't want to dox myself again. So, basically just going to wait here. Hooray. And figure out if this is going to work for us. If it doesn't, then, and if nobody else shows up, then I might just switch this to be a game stream, because why not? Yeah, and I already did a math stream on Monday. I'm sorry, Matthew, I don't want to disappoint you. However, yeah, if this is not actually working fairly soon, I'm gonna have to abandon the project for tonight. So tonight, yeah, some apologies are in order, but I needed to actually go and get food at some point today for the family, and I decided to, just put it off until after after my son was in bed. So unfortunately, that meant, I had like an hour, hour and a half to do it. And that certainly wasn't going to happen. So, a grocery shopping trip for me rarely lasts under 2 hours. So, I think tonight I made it home just before 9:30. So, made some decent time, I guess. So last time we were talking about the mass and density physical applications, as well as work and force for both, well, for pumping water. The same idea occurs, or the same idea goes with when working with springs as well, or cables. So the amount of work necessary to lift an object by a cable, and the amount of work done to compress a spring, or work done on you to release a spring. Alright, this is not my fault, right? Oh boy. Yeah, OpenStax is also spinning at the moment, which is really weird. There we go. No, that's 2.5. What are the other one? Tonight I am migrating over my entire Steam library to a new SSD. That shouldn't have any effect on the whiteboard, as I believe that is an entirely different drive. But that may also be part of the problem, I don't know. you go. I'm only an hour and 10 minutes getting to this point, so, you know. Great. So tonight, I'll probably skip the hyperbolic functions and calculus on, and we can talk more about integration by parts. I think is going to be the best thing to do here. Okay. So I said before, when you're doing integration by parts, when you're trying to prove it, you'd want to start with the product rule. So we had that h of x was equal to f of x times g of x, the product of two particular functions, and when we wanted to take the derivative of all of this stuff with respect to x, we would then say that we had dh dx equal to, and then here the product rule was df dx times g of x plus f of x f of x times dg dx. Yeah, I'll take that back out. Come on. And it looked a little bit better when we made this h prime is equal to f prime at x times g of x plus f of x times g prime of x. So if we take this and then we reverse it and take the integral of all of the pieces here, you might say, well, we just did the other thing, so clearly it's just going to become the original product rule that we had up above. Well, Yes, in theory. However, what we can do is show that this is a little bit easier to work with. If we make this the original, right? This is h of x, but that's then f of x times g of x. And that is set equal to integral of f prime of x times g of x plus, let's do dx, right? And we're going to separate the integral on this side because we have addition in between, plus the integral of f of x times g of x dx, g prime at x dx. All right, now if we solve for the second one and let f at x be u, g at x be v, and therefore du dx is equal to f prime at x, and dv dx is equal to g prime at x. If we kind of manipulate this around a bit, kick all the dx's over to the right-hand side, this means that du is equal to f prime at x dx. And therefore, same thing here, dv is going to be equal to g prime at x dx. So we see both of those pieces here and here. How am I doing? I'm clear. Good. Alright, so that means that f times g is now going to be u times v. Is equal to, here we have integral of g of x is v times f prime at x dx is du plus integral of here f of x is u and g prime at x dx is dv. Alright, now if we just solve for what we have here, that means we're going to take this one and move it to the left, which means we are going to get, that's good, can't see my cursor over there. Alright, this means we're going to get uv minus integral v du is equal to, over here we have integral of u dv. So this is our entire point behind integration by parts. As many of you know, I hate just using a formula and coming up with an answer. It doesn't really make sense to me. So understanding this whole process, we're really using the product rule for derivation and then taking the integral of everything to walk it back. And again, we don't just walk it back. We want to take it and turn it into a completely different form. So the stuff that is, let's see if this will do it. Nope, still can't see. Cool. Oh well. So we want to solve for one of the integrals, and therefore any sort of integral that has the form integral of u dv can then be traded for uv minus integral v du. It's a very powerful method. We've already seen it in action a couple of times. Something else that happens occasionally, and I think we might have done one example that did this, but if we needed to take, for instance, the integral of e to the 2x times cosine of x dx, in this particular case, there isn't one particular section of this, which if you take its derivative is going to start de-escalating. So in the case of something like integral of x squared cosine of x dx, we would want our x terms to be the u stuff, and then the cosine of x times dx would be the dv stuff. When you do this, this is going to de-escalate the u down through all of the subsequent lower powers as you take its derivative over and over and over again, because we need du in the future stuff. So if we were to do that here, what we would see is we would get uv, so u is just x squared. V is the integral of the cosine of x dx, which is just the sine of x, minus integral of v, which again is sine of x. Du in this particular case is going to be the integral, the derivative of x squared, so it's going to be 2x dx. All right, and then this integral also cannot be done. Oops. So we have x squared sine of x minus, bring the 2 out, integral of x sine of x dx. Sine of x dx can be dv, and x can be u, just as we had before. So x squared times the sine of x minus 2 parentheses, and now uv is going to be x times v on this second step is going to be the negative cosine of x. Right, and then we subtract the integral of v du, which is going to be a negative cosine of x times the derivative of just x is going to be dx. So we get x squared sine of x minus, here the first term is going to be a plus 2x cosine x, and then we have a this is always fun, we have a negative and a negative here, which are going to divide out or multiply out, and we end up with the integral of cosine of x dx is just sine of x, and then we multiply by the negative 2 out front, so a negative 2 sine of x. Alright, so that is set equal to all this stuff from the very top. So the integral of x squared cosine x dx ends up being x squared sine of x plus 2x cosine of x minus 2 sine of x. Alright, what about this one over here? When we introduce this e to the 2x term, now we can't actually knock down its exponents to become lower powers. So when we take the derivative of either of these, they're going to be cyclic in nature. E to the 2x is going to be a one cycle, in that it's just always going to be some number times e to the 2x. So if you take the derivative, it just keeps cycling back to itself. If you take the derivative of the cosine of x dx, this is a 4 cycle. So it's going to take 4 derivatives to get back to where we started from. So neither of these seem terribly appealing, but hey Matthew. So if we take the derivative on the first one and then the integral on the second one, so let this be u, let this be dv, just by default. That means that du is going to be 2 e to the 2x, and v is going to be, again, the sine of x. Sorry for being late. Had to go get food for the family, and groceries wise, not just dinner. So I ended up being significantly late, but had to be done, unfortunately. One second. So yeah, anyway, yeah, I'm just magically in Central Time Zone now, so it's fine. Anyway, yeah, I was just messing around with integration by parts, making sure I'm understanding where we're coming from here. So yeah, this started with product rule. So with one like this, it doesn't actually matter which one you do for derivative versus integral. Usually I think I like sticking with integral being the e to the 2x, because here it's a little bit easier to, like, I don't know, it makes fractions, so some people don't like that, but at the same time taking the integral of trigs sometimes gets people a little tripped up. So it kind of goes either way. I'm just going to go this way for now, but uv is going to be e to the 2x sine of x. So how's things? Minus, here this is going to be the integral of v, the sine of x, times du is going to be 2 e to the 2x. So actually, go back a little ways here. 2 e to the 2x dx times the sine of x. Right, and then you notice that, okay, well, this can't be finished here either, so we're going to have to do the same thing again for this one. This is going to be a minus 2 integral of e to the 2x sine of x dx. Let, again, e to the 2x be u, sine of x dx is going to be dv, and then do integration by parts again. So when we do this, we get negative 2 times the quantity Here, u e to the 2x. V is going to be the integral of sine of x dx, which is going to be a negative cosine of x. Alright, then minus integral of v du is going to be that negative cosine of x again, with du being another times 2e to the 2x. dx. And that's still going to be e to the 2x sine of x. It's just going to keep carrying down. And here, this is going to be a negative 2e to the 2x. This is a negative, multiplies, makes that a positive 2e to the 2x times cosine of x. Then here we have a did I do that wrong? Oh, yeah, this is fine. So this is going to be a negative 2 times this positive is going to make a negative 2 integral of, this is actually going to multiply by 2 again, so this is going to be a negative 4 integral of e to the 2x cosine x dx. The other side over here is the integral of e to the 2x cosine of x dx. And as luck would have it, we have both of these things on both sides. So we can add 4 times that given integral to both sides. And then this becomes 5 times the integral of e to the 2x cosine of x dx. I mean, what are you curious about? E to the 2x sine of x plus 2e to the 2x cosine of x. So then the integral of e to the 2x cosine of x dx is equal to 1/5 times e to the 2x multiplied by parentheses sine of x plus 2 cosine of x. So one of the things that we can do here is start leveraging interesting properties of integrals and just interesting properties of integrals to be able to say, all right, here's what this is going to be equal to. And this happens a lot when you're talking about like any sort of cyclical patterns. So e to the x, trig functions, all sorts of functions like this are going to end up in some sort of cyclical pattern, and then eventually when the cycle returns back to itself, that's when you can say, okay, combine the stuff that has all like terms, all like integrals, in fact, and then the rest of it is your answer. Large finite numbers and operations beyond exponentiation. Oh boy. How large are finite numbers? And which beyond exponentiation? 11 many factorial. Yeah. Yeah, factorials are fun. The way that they mostly work is just saying, like, let's work with combinations of things. So how many different combinations can you make with, 3 objects? So that's going to be 3 factorial, because when you have 3 objects, A, B, and C, and you'd like to know which, or how many different arrangements there are, that's when you start looking at factorials. So, so here ABC is going to be the first one, ACB is going to be the second, then you switch to B, ACB, CA, C, AB, and CBA. If you consider them all different arrangements, then yeah, these are basic combinations. I guess these technically are permutations because, yep. Because all the different arrangements are different from each other. So in the world of combinations, these are identical to each other. You've picked an A, you've picked a B, you've picked a C. But in the world of permutations, they're all different. Yeah, so here with 3 factorial, basically you're saying, all right, I want 3 objects, and then which one am I going to put into each one? So I could do A, I could do B, I could do C. Or if I'm saying I'm going to pick where A goes first, then I have 3 possible places where A could go. Then if I want to do B second, well, depending on where A has gone, now I only have 2 possible locations for that to go. So that goes in there, and then there's only one possible combination for one possible location for C to go. So that's going to be 3 options for your first choice, 2 options for your second, and 1 option for your first. Yeah. So algebraic properties get a little awkward. Let's explore, because I don't remember a whole lot of this besides what we did in my Combinatorics class in master's level, but I don't remember a whole lot of it. So, like, yes, they do divide very nicely. If you wanted to say, like, what is the permutation, how many permutations are there of this list? Then what we're looking at here is going to be like 3 factorial factorial. So we took 3 factorial to get this permutation list. And then we want to know how many different permutations does this list have. So like you'd start with ABC and then arrange all the other 5 in different orders. Again, this ends up being 6 factorial, so 6 times 5 times 4 times 3 times 2 times 1. And that should be 720. Yeah. So they're commutative. Right, that much is easy enough. Because each of the individual lists are all multiplication, then the lists themselves can be swapped by a commutative property of multiplication. Same thing's going to be true for addition. So it doesn't actually matter in which order these are arranged. And again, if you just think of them individually as numbers, then clearly, right, you're able to do additive commutation or multiplicative commutation because these are just numbers. And then in this space, you can also do those operations on numbers. Sorry, those numbers have those properties. Therefore, the properties extend to factorials. Is there such a thing as associativity? I guess it just wasn't the thing I was thinking of. So associativity is going to be a thing. It's just that it's a factorial times b factorial times c factorial on the outside is going to be equal to a factorial on the outside times parentheses b factorial times c factorial. Yeah, so that's going to work. No, keep in mind, it's not that the groups are being factorialed. I was thinking about that, like, oh, well, associativity for factorials should do something like this, where you say, like, okay, this is going to be equal to 3 parentheses that doesn't mean anything. So I got dead-ended there. Right, the problem is that the argument of the factorial has to be a number, and it's the number that comes directly before it. So factorials are then, therefore, going to just be yeah, let me know what you came up with, if that. Yeah, well, the 4 and the 5 also then cancel out if you're going to divide. Or specifically, you're just talking about the 6. That's just eventually going to become 3 factorial. 6. Right, so the 5 and the 4 from the top are also going to be gone. So let's do that here. Technically the 1, but you know. So not necessarily. The sorry. I mean, you could extend it to try to say what would happen if we just did like 7 factorial or 6 factorial. Then since the top number is a prime here, that's not really going to do anything. 8 factorial over 7 factorial. Here you could take out, right, so this is here you want to take the top number and do something with it. So the 8 here can get rid of the 4 and the 2 in the denominator. Alright, and then the top numbers are also could also go away here and here, but now we're left with 4 factorial over 3. So, yeah. I think it just works out nicely for that particular one. Just because, you know, the highest number was 2 of the previous factors, and when you took them out, and they were consecutive, so that helps, then it was able to like blow holes in what was left of the other factorial. Alright, the other option for associativity here was like had it. No, no. So it has to be symmetric. The associativity has to be symmetric, where you have the A, the B, and the C terms, which all do something there. so associativity of the operation may not be a thing. Oh, man. Oh. I hope my kid train this morning for a mini triathlon that she's gonna do. So I mean, it's not like it's actually big or anything. It's just a 100-meter swim, which I mean, she's like 8, so 100-meter swim, 2-mile bike ride, and a half-mile run. Which again, for their size, it's gonna take a while. It's gonna take some doing. She's pretty good at it. Only just started. Only just found out about it a few days ago. So she was like, "Yeah, let's do the bike ride part." And I'm like, "Okay." Gotta get myself off the couch. Nice cold showers when we got home. Ugh. Yeah. Well, I mean, as long as you're not like really pushing it hard, you should be more or less okay. Unless you also have a predisposition to having torn ACLs or LCLs or anything like that. I fortunately do not, but I have. Yeah, that can also happen. Yeah, I mean, human beings were only supposed to live for like 30 or 40 years as far as evolution is concerned. So, I'm blurry. I think I'm alright. Yeah, I've been doing a form of karate for 15 years now, um, which I only started after college. So I'm like way behind the curve. But yeah, it can be hard on the knees, can be hard on the bodies, but well, I mean that is the eternal question. Everybody's going to be stuck on that forever and ever and ever because there isn't really a single like point to everything. It's over my not so many years. Um, I mean, you know, still significantly more than some other people, but I'm still on the upper side of a third of that person's age. Um, when I was probably about 24, I was sitting down and I came up with the idea that basically everything in the universe is just set to improve. Like, to try to improve over its existence. Otherwise, it just goes away. And I mean, basically, it's evolution. But, I mean, life always tries to find some sort of way to create a structure out of the energy that it's being given in order to preserve itself, in order to ensure that it continues on. Um, Whereas entropy in the entire universe is just trying to spread all energy out evenly. So I had read a bunch of Richard Dawkins. I'd read some of On the Origin of Species by Darwin. Mostly I absorbed most of it off of ironically. So that's the other thing, is that I actually am of the opinion that life is natural, not just for the obvious reason that we are in the universe, but no. So entropy is an overall force that you can only look at it within a closed system. So if you want to talk about a closed system, you could talk about, for instance, a perfectly sealed box, or let's say the entire universe. Even something as small as, lol, our solar system is not a closed system. The energy from the sun keeps going out, radiates outward, and has hit, every star system around us. That energy is continuing to dissipate. We also, likewise, are receiving energy from outside, which is not equal to the sun's output. So, and the energy input from those sources is minuscule. You're not going to run solar power off of stars, so off of other stars. So life really is just like, you can't talk about it as, oh, it's a counter argument, because, well, no, over the entire universe it still eventually will spread out its energy, right? All life eventually dies and spreads its energy out over a certain area. This could be fun. So when you're thinking about, life and entropy and things like that, you got to remember that the Earth is still powered by the sun, and um, all of the energy that's hitting us is giving us, making us gain energy from whatever position we were in. So this is a bit like the physics problem with the ratchet car, where if you have this like infinitesimally small teeth on the ratchet and a gigantic wheel that is, has a very low mass somehow and attached to the car, if the car is bombarded by radiation, it could very well start moving the car up the hill. Does that mean that gravity doesn't work? Well, no. It's just that whatever particles are bombarding this car with an infinitesimal ratchet, the ratchet is preventing movement backward, and the this is a physics problem that we were talking about in like my physics class, or we had a seminar. So physics seminar was all the physics majors just getting together and talking about problems in physics. So if the wheels had sort of a ratchet system, it's going the wrong way, isn't it? All right, and these ratchet teeth are like infinitesimally small. So as just particles, yeah. You probably have one of those as a screwdriver. So the socket set. So it's an object which will allow a tooth, no, a hook to move upward along the ratchet as long as the system itself is moving this way. And then when it clicks into place, when it hits the next tooth, what happens is that this will end up being, your tooth will end up being over here. It's still going to keep turning this way, but then if so like this drops into place so that if there's a force going in the other direction, this is going to lock it here. So it's just going to hold it in place and prevent any sort of movement in the opposite direction. But then, some other tooth will come along and allow this to knock up and then go over the top. And yeah, more or less. There is the possibility that a hook here will go up a tooth about halfway and then back down again. Right? But it'll get caught on the previous tooth. So we were doing this thought experiment where if you have a ratcheted wheel on this car and it just gets bombarded by particles, which are so tiny they impart almost no force upon the car, but it's non-zero. Then what happens is like you still get particles which are going to bombard the car from this direction, but they don't do anything. Unless they are exactly paired up with something over here, this car will appear to move uphill. Right, so just imagine for a second that you're just pushing the car, right? So if you're just pushing the car, then you are imparting a force upward or forward into the hill, which will then translate into a forward motion up the hill as long as you are pushing this with enough force that it's going to knock one hook over one tooth, right? As long as you can get it over the next tooth and over the next tooth and over the next tooth, then you're going to eventually have some sort of forward motion. If it's a car, right, thing that weighs a couple of tons, it might be hard, but you could do it. So if you just have like particles bombarding the car, then you could impart a minuscule force on the car, not a macro force like we could, where we can push, a few hundred newtons or something like that. It doesn't do much to the car, but it does do something. Well, particles, it's sort of the same. It's getting bombarded by particles. If it's just coming from one direction, then it ends up being something like the person who's pushing the car, but it's like, even tinier. If particles are bombarding the car from all directions, then technically, if the forces don't perfectly cancel each other out, if like one of them hits now and the other now, right, if they're asymmetric in any way, then what's going to happen is that the forces imparted upon the car will not be symmetric. And if the teeth were infinitesimally small, right, some ridiculous amount small, then what would happen is even just like a single particle hitting the car could potentially move the car forward like, 1/1 billionth of an inch or something like that. So then getting hit from all directions by all of these different particles, the car could, in theory, still move uphill. Now again, it would take practically forever in order for it to do that, but, little by little it would add up. So tiny, tiny particles and tiny amounts of particles would eventually add up to a macro movement. So the same sort of thing is happening with like evolution, wherein, every generation that goes by, there are changes across the board to nearly every organism from one generation to the next, right? There are different combinations, different permutations of our DNA, all sorts of stuff. Going back to like the beginning, where there was probably not anything you would call life, primordial sludge, all that stuff. Anything that was able to survive was then able to propagate further. Everything that did not survive was just either a bad combination or had a bad series of events happen to it. And that combination was removed from the gene pool. Yeah, I mean, again, we're not talking necessarily life, this, or anything that we might call life. This is like, going back to, I mean, hell, just look at viruses these days, right? There's all of the changes that happen from one generation to the next, or even over a few hundred, a few thousand generations, with a virus can happen very shortly, like in a very short amount of time. In an organism like us, we're so big at this point. We're so big at this point. We have so many different backup systems inside of our bodies, which, like, from the beginning, will determine whether or not a pregnancy is viable, and then will self-terminate if it is not viable. And this could be, it's not a single gene which is doing this. It's just a series of like safety nets to make sure that any life that is born at least has like, some baseline ability to survive. Yeah. I mean, hence why we don't all end up the exact same, clone over and over and over again. Um, if the nets were infinite and infinitely awesome and could catch every single mistake and could redirect all mistakes to like something that was better for the organism, or else could I mean like if every single organism could have the exact same. Oh, yeah, yeah. Yes, there you go. Yeah, I mean, there are a finite number of nets because we have accumulated them over time, and so they are actually countable. You would only be able to count them out and say, like, okay, at some point between here and here. Like, the nets themselves are also not conscious, but they can do work which a conscious being could potentially say, like, oh, look at that. Like when you look into mirrors reflecting mirrors, or something slightly less literal. So you're gonna find a hard limit based on the neuronal output of the brain, but you know. Right, so the metacognition, being able to think about thinking about thinking about thinking about thinking about something. So I think I'm probably gonna have to duck out here pretty soon because I am like on the verge of passing out. So uh, Yeah, well, it was mostly because of the also true, utilitarian. Yeah, it was also because of the you know triathlon practice that I helped my kid with, and then I just been up since I don't know 7, whatever, which it's not too bad, but still it's 7 to 2300, so we're getting on 16 hours here, and I have been very much very well known for staying up way 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 too late. So yeah, I'm also transferring all of my stuff to an SSD right now, or I should say, all of my Steam library moving over to an SSD, so that if there's any like SSD quantum shenanigans, um, I can just hit, you know, do a verification on all of the games or on this game's assets, and it'll do it. Whereas if it's a like Word document, it would just come up with all sorts of holes in it. So yeah, so I'm gonna um yeah, the whole, so there's the whole quantum tunneling thing, which once you start getting electronic um, electronic pathways that are so close together, then occasionally some electrons can jump the gap between the two electrical things. Yeah, it does actually happen. And this is why solid state drives corrupt over a certain amount of time, in particular. It's like compared to your standard spinning disk um, hard drives, SSDs will go bad faster. So those electronics are small enough to occasionally have a quantum tunneling event with some of the electrons. It's not often, but over the period, I think it says right on the drive that it basically has a 5-year shelf life. So, like all the information that's on it, it'll last 5 years. So basically, I'm transferring anything that is verifiable via the internet, or anything that I'm not going to use for very long, but I need like pretty quick access to it. So I'm going to trade over my video drivers. I'm going to do all of my, yeah, like some of them might not have the architecture for it, and it might end up being like, it's fine. But generally speaking, yeah, solid state memory does not last as long as hard drive memory, um, spinny disk. So like all of my documents, all of my like, you know, my super important stuff that I'm using, all of that is going over onto or staying on my drive, my disk drive. Yeah, but at the same time, like I said, the only thing that I'm putting over there is stuff that I'm going to be able to verify. So the everything in Steam, um, drivers which are updated on a roughly monthly basis, so it just gets rewritten over and over and over again. That stuff's gonna, just because it's getting rewritten, it's not going to um, it's not going to like decay. It's not gonna have time to decay. My Steam games, some of them I have not played in 4 or 5 years, and so I just need to re-verify all of the assets, and then they'll be fine. But yeah, with this, I was actually really surprised. It's only a 2.5 inch thing. I was like, oh yeah, 2.5. That's like you know, the drive bays that you'd stick in here for 3.5 inch floppy. You're still gonna have to use like this much space, but the disk only takes up this much, right? No, no. It's literally this big. It's smaller than a floppy disk that gave us the save icon. Like, it's smaller than that. It's literally this big. And like wafer thin. I was like, oh, huh. I guess I should have been expecting that. So I've got nowhere to like dock it inside my entire tower. There's no docking. I'm just like, So I just kind of like put it where the old, or put it like kind of up where the disk drive is and just set it down. Let's hope it doesn't move around too much. All right. So I'm gonna shoot a raid over to Jason Charles Miller, that music guy. So he's actually streaming tonight. So that would help. I'm not on Stream Manager, so yeah. So I'll shoot a raid over there, and I will catch you. You know, what, latest next Wednesday or something. But yeah, I'll catch you later. We'll talk, and let me know if you have any more questions about weird or cool or whatever stuff. And in the meantime, I'll see you later. Anybody else who's out there, thank you very much for coming to VOD and sticking around through whatever we've got here. So if you have any questions, please let me know. My email address, nsimplexpachinko@gmail.com, is available and open to anybody who wants to send in questions. And I will try and get to them as I can. So, thank you everybody for coming. My name is Obi-Wan Pez. This is NSimplex Pachinko. Have a good night.